So let's start looking at this thing called integration. And we're going to start by solving a problem, and that is, how do you find the area under a curve? Now, if it's a nice regular shape, like a straight line for instance, it'd be easy because we could say, oh, that's a triangle or a trapezium or whatever shape it is, and we could use the formulas that we know. But something like this, a cubic, we don't have a formula for that. So how on earth are we going to do it? The best I can do at this stage is estimate, and obviously this will be a terrible estimate. And so I'm going to estimate with a couple of rectangles and say the area under this curve is going to be the same as the area of these two rectangles, and clearly I can look at it and say, well, I know actually it'll be less than whatever this amount is. So whatever 1 times 1 cubed plus 1 times 2 cubed is, I know it'll be less than that. What I've drawn there is what we call the outer rectangles or the outside rectangles. But I could also draw inner rectangles, some that go underneath the curve, and actually the first one's not really a rectangle, it's just a straight line, so it's got a height of 0. And I know that the area that I'm looking for will be bigger than that, so I can trap the area between these two numbers. We get it's between 1 and 9, and I guess the logical thing to do, the thing we automatically do when we say, oh, well, it's somewhere in the middle of these two things. So middle, what do? We'll find the average and go, okay, well, I reckon the area is about 5. Turns out the exact area is 4. Close, but not that great. Well, I can make it better by doing more rectangles. So instead of doing 2, there I've got 5. Still an overestimate, but the overestimate's going to be smaller. So in this case, there they all are. It's going to have a width of 0.4 each of them now, and the height of, well, whatever the x value is cubed. And so now I know it's less than 5.76, and if I do the inner one, I know it's going to be more than 2.56. Average those, 4.16. So just from going from 2 to 5, I've got a lot closer already. So all right, what the heck? Let's do 10. So it's less than, well, that turns out to be 4.84. And if I draw the inner ones, and that turns out to be 3.24, average those and I get 4.04. So clearly, the more rectangles I use, the better trap, if you like, or sometimes people call it sandwiching the value, trying to sandwich it between two values. All right, so let's look at this idea in more detail. We now know that as those widths of the rectangles get smaller, my estimate's going to get more accurate. So I'm just going to look at one of these. So I've gone from y equals x cubed to just some random curve y equals function x. So there's one of those rectangles. Well, it's not quite a rectangle when you look at the top, but I'll explain in a sec. I'm going to create this new function. I'm trying to find a function that will find the area. And so I've defined area C to be the area that's going from 0 to C. So area x will be the area that's going from 0 to x. So the area of my shape there is going to be the difference between those two values, whatever they turn out to be. So that's going to be the area. Well, it's not a rectangle, but I could estimate it with a rectangle. Depending on which way I draw the top, it could be an overestimate or an underestimate. Now, the way to make that overestimate and underestimate the same is to make the width of the rectangle 0. Now, clearly we can't do that. But using our idea of limits, we can investigate what's happening as that value approaches 0. So we know it's approximately going to be the difference between x and c times whatever the function value happens to be. So rearranging that, I now know that the function of the curve will be equal to this area function I'm trying to find minus area c over x minus c. I'm going to rewrite that and say, well, let's just call the width of the rectangle, which is x minus c, I'm just going to call it h. And so it becomes area c plus h minus area c over h. Interesting. But what I just said before was as that width gets smaller and smaller and smaller, we get more accurate. So if we can investigate the limit as h approaches 0. So I now know that the function of the curve, and we know that equation, whatever the equation of the curve is, then the limit of as h approaches 0 of the area function that we're looking for minus area c over h. And that looks awfully familiar. But here's the clever little trick. I'm going to rewrite it. Because if h is approaching 0, c and x are approaching the same value. So instead of calling it c plus h, I'm going to call it x plus h. And instead of calling it c and the other one, I call it x. And now that really is familiar. That was our first principles formula for the derivative. So what we're now saying is the equation of the curve is in fact the derivative of this area function that we're trying to find. So now we actually know the formula, because all I've got to do is go backwards, which was finding, if you recall, the primitive function. So the equation of the curve is the derivative of this area function we're looking for. The symbol we use for integration is the long S symbol. S for sum, basically, is what it's there for. So we're saying sum. So we're going from A to B of function x. And we know the answer to that will be the primitive function. We'll substitute in B and we'll substitute in A. Because remember, it was the area going up to here minus the area going up to here. We can now find our area. So all right, let's go back to that question we had. X cubed. How did I know the exact value was 4? Well, I could say that the area is what we now call the integral. The integral is the primitive function. And you hopefully recall how we find the primitive function for a polynomial. Add 1 to the power over that new power. So it'll be a quarter x to the power of 4. Notice my notation. I have integrated. So I now put square brackets around it, and the values, I'm going from 0 to 2. We always substitute the top value in first. So all I've got to do is substitute in and do a calculation, and there it is, that exact value that I got before of 4 units squared. 4 units squared. So I get something like this. Okay? Well, all it's saying is, hey, go and find the primitive function of x squared plus 1. That's a third x cubed plus x. Substitute in 3 minus substitute in 2. What's the answer that you get? And the answer is 22 on 3. Notice on this one, I did not write units squared. The area is an application of the integral. So in the first one, yes, I was finding an area, so I put the units on it. The second one is simply saying, hey, find the value of this. So I don't put units down. So it's 22 on 3. Negative powers, it's still the same idea. Add 1 to the power over the power. Just be careful with the negatives when you're adding. And you'll notice, for the sake of substitution, I changed mine into 1 on x squared there. I just find that easier to substitute in and come up with an answer. We get 9 on 800. Here's an interesting one. d dx of the integral of function t to t. What is this saying? Remember the notation for differentiation? And one of the ways we could write it is say d dx of whatever the function is that we're differentiating. So instead of writing dy dx, I could write dx squared dx, and the answer would be 2x. So this is saying differentiate this integral. Well, differentiation and integration are inverse operations. So they cancel each other out. So when I go to find the primitive function, that's what it's really saying. It's saying, okay, differentiate the primitive function, but you're going to substitute in x and you're going to substitute in c. That's what you're differentiating. Well, so let's do that. Substituting function. Function c is a constant number. So when I differentiate that, I'm going to get 0. So really, I'm just differentiating the primitive function. Well, hang on. If you differentiate the primitive function, you must come back to the original function. And so I get function x minus 0. So to generalise that, we know that when we differentiate the integral of going from c to x, we just get function x. The value, the letter here doesn't matter because we're substituting into it. So it goes away anyway. It could be function anything. Alrighty, there's a starting point for this year.